Thank you very much, Professor Chen, for the very good introduction to me. And I'm very happy to have Professor Chen, Professor Pachapulu, Professor Wu, and Professor Wang for serving as the committee members. I'm glad to have you here today. So today, I'm going to introduce my research on cross-domain and behavior-based user authentication in mobile edge and IoT. So what are the mobile devices? Mobile devices such as your smartphone, wearables, and smart pads. These devices are connected to the internet and serve as your end device. We call them as mobile edge device. And what are the IoT devices? These are devices that develop in our home and offices, such as voice assistant device, smart TV, smart home appliances. The market size of mobile edge and IoT devices are gaining rapid momentum in recent years. Therefore, user authentication, the process of verifying the identity of a person who connects to this mobile edge and IoT, is become increasingly vital. Mobile devices such as smartphones and tablets inevitably contain private and sensitive information. For example, to facilitate various applications, this device would store information such as contact lists, emails, messages, credit card numbers, and merchandise ordering information. Unauthorized access to this device would put huge amount of sensitive information at the risk of misuse. In addition, current mobile IoT devices are exploring the ability to perform voice recognitions. By using voices as input, users can smoothly and conveniently interact with their voice assistant systems. Such a convenient functionality has been widely adopted by users and used in many applications, such as playing music, shopping online, managing calendar events, and controlling smart home appliances. The significant financial benefits of using such voice commands lure adversary into faking the user's voice comments and get credentials, making unauthorized purchase. We need to protect such attacks. Well, what have been done for user authentication? Traditional user authentication scheme mainly rely on password and graphical patterns, which suffer from various attacks, including password theft, shoulder surfing, and smudge attacks. Biometric-based user authentication opens up a new pathway to secure mobile device. For example, fingerprint-based and faceprint-based solutions are widely used in many premium phones, such as iPhone and Samsung Galaxy phones. They offer a more secure way to access mobile and smart devices. Voice assistant systems mainly explore users' voice to perform user authentication. They mainly based on acoustic features extract from microphone data to identify users, such as voice timbre, vocal check, resonance. But such approach have been proved to be vulnerable to many acoustic attacks, such as replay attacks and hidden voice attacks. To add another layer of defense, some VA systems explore a second factor to secure voice comments, such as challenging questions, replay message, calls, or virtual buttons. But this approach will require significant user effort and could be prone to user careless behaviors. To support the evolving concept of user authentications, this dissertation aims at investigating using built-in sensors readily available on current mobile and IoT devices to perform hard-to-forge, low-cost, and easy-to-deploy user authentication. The design solution can be used along with existing authentication scheme, such as voice authentication and face recognition to provide enhanced security. Here is the roadmap of this dissertation. I will first briefly introduce 3 projects which has been introduced in the previous proposal. Then I will focus my work on using Wi-Fi signals to perform behavior-based user authentications. Then I will introduce 2 future research projects, including speech privacy attack via Phased-MIMO Radar, and also voice authentication on AR/VR systems. So I will first introduce security vulnerability study in intelligent voice assistant systems. So with the widespread of voice assistant systems, the vulnerability of this system against various types of acoustic attacks have become rising security concern. For example, replay attacks which attempt to bypass authentication, simply replaying the user's audio sample, has long been one of the dominant source of audio spoofing attack. To increase the attack seriousness, adversary can even launch imperceptible or inaudible voice commands. The attacker can launch hidden voice attack or ultrasound attack, and such attack leverage the perception gap between human and machines, making them highly stealthy. So we find that to defend this attack, we find that the current mobile and IoT devices are equipped with microphone array that bring several benefits against attack detections. The multi-channel audios encodes important spatial information that is harder for the attacker to manipulate. In addition, the voice assistant systems also come equipped with a multi-channel microphone array, so they're readily available. Motivated by these potential benefits, we designed a holistic solution to detect various machine-induced audio attacks, leveraging a multi-channel microphone array that are available on voice assistant systems. So our solution is to first operate on the multi-channel audios. We first process the raw waveforms through extracting short-time frequency transformation heat maps. Then we design two neural networks according to different usage scenario, a Type 1 network, which is a large and powerful VGG network, and also a Type 2 network, which is a fast and lightweight network, to differentiate the user's sounds and also the attack sounds. In addition, because the performance of learning-based predictive models are likely to degrade if the testing sample is collected from a new environment, we introduce a domain discriminator network during the training phase to learn environment-independent features, so as make a model is effective in different acoustic environments. The next project I will introduce is CardioCam, a cardio biometric-based authentication by using mobile cameras. So in this project, we designed CardioCam, which is the first hard-to-forge, low-cost user verification by using cardio biometric extract from the built-in cameras on mobile device or IoT applications. We demonstrate that intrinsic, unique, and non-volitional cardiac properties can be preserved when extracting the cardiac feature from the user's fingertips. The cardiac biometrics are well captured under the reflect light on the built-in camera when the user pressing his fingertip upon. So, as illustrated in this figure, our system simply requires the user to press his fingertips on the camera surface for cardiac feature extractions. It illuminates the fingertips with the flashlight on the camera and then explore the built-in camera to continuously observe the variation on light absorptions, which is introduced by the cardiac features embed. There are existing studies on using dedicated PPG and ECG sensors, but compared to this approach, we can directly apply our system on a readily available mobile device. So in this work, we extract systolic features from the cardiac waves to characterize the cardiac motions. We localize the inflation point by searching for a local maximum and minimum within each cardiac cycles. And normalized time intervals will be our cardiac features to represent the user's identity. Next, I will introduce our cross-domain voice authentication system for voice assistant system. In this work, we design a low-effort, training-free user authentication system by leveraging aerial speech vibrations. Our idea is to leverage wearables accelerometer to harness aerial speech vibration corresponding to live human speech. The wearable devices are usually worn on user's body and rarely left unattended, so it is natural for us to leverage such pervasive personal device as a token device to facilitate voice command authentication. Our system leverages two domains, which is cross-domain, to perform authentication. So first, when a user gives a voice command, our system will explore the motion sensor on the user's wearable device to capture aerial speech in the vibration domain. Second, the same speech can also be captured in the audio domain via the VA device microphone. By comparing the vibration domain signals triggered by the aerial speech and also the audio domain of the microphone, our approach can verify a voice command on the VA system's clouds without any training. The system can be easily integrated with existing VA systems and wearable devices without making any hardware modifications. So next, I will introduce our behavior-based user authentication using Wi-Fi-enabled IoT. This will be the main focus of this dissertation. So we aim to design a device-free system that can verify the user's identity through daily activities at smart space. We would like to utilize the Wi-Fi signal generated by mobile and edge device, IoT device to achieve this goal. And our system should be able to recognize the user's identity through daily behaviors without any interference to the user's daily activity. The system also should support the continuous user authentication and can be integrated with other techniques for multi-factor authentication. So what is the insight of our approach? Our approach is based on two observations. First, the user's physiological characteristics such as body shape and height are unique for each individual and can be used for identification. And more importantly, the human's unique behavior characteristics inherit from their daily activities, such as gesture preference and walking gaits, can be used to differentiate user. So this observation has been validated by many existing work to recognize the user's hallmarks through wearable sensors attached to the user's body. However, such approach will require the users to wear a device all day around the clock, which will introduce overhead to the user. So in this work, we aim to design a device-free user authentication system. The device-free here means that we do not require any additional sensor attached to the user's body. We aim to use Wi-Fi signals generated by regular communications to facilitate authentication. In the past decade, the smart environments have incorporated Wi-Fi techniques to provide increasing wireless communications among the application and mobile device, such as voice assistant, smart TV, smart refrigerator, and smart glasses. It is thus natural to explore wireless signals ubiquitous in these smart environments to derive inherent biometrics to authenticate users in a convenient and device-free manner. So we propose to extract representative features based on both amplitude and relative phase of channel state information measurements, which are readily available in Wi-Fi signal. The channel state information describes the properties of signal propagations, such as scattering, fading, power decays, and multipass. We show the extract CSI amplitude of a subcarrier over time when the two users are walking and opening a cabinet. We can see in these two figures, the CSI amplitude is capable to capture unique characteristic of users walking. But we also find that such uniqueness is not significant if for the activity of opening a cabinet, which only involve a small scale body movements. So besides extracting CSI amplitude, we also propose to extract CSI relative phase to capture the user's uniqueness. As shown in this figure, the transmission path between the transmission path of the two different transmission paths of M1, M1, and M2, there is a delta T. So the delta T, it represents the distance transmission distance from the same transmitter to two receiving antennas. This will result in a relative phase shift. We showed in the formulation that the relative phase shift delta D is the length between the two transmission paths, and lambda is a signal wavelength. Because of the centimeter level lambda, the relative phase is capable of capturing more subtle movements of the user compared to CSI amplitude. We show that the relative phase of walking and opening a cabinet in the following two figures, and we can find that the activity difference between more discriminable when we applying the relative phase. So in our system, we first preprocess the raw CSI measurements with phase unwarping to unwarp the relative phase. We first eliminate the relative phase error on each subcarrier. We can see in the first figure, the time series raw relative phase and the three subcarriers has observed some discontinuity when the relative phase is approaching pi. In this case, we can use phase unwarping to eliminate such discontinuity and show the corresponding relative phase streams in the second figure. And we can see that the discontinuity is disappeared. In addition, even after the data collaboration with phase unwarping, some subcarriers still contain a lot of ambient noises. To ensure the reliability of CSI measurements, we propose a subcarrier selection scheme based on the correlation between neighboring subcarriers. The two figures present an example showing the score of four subcarriers. We can observe that CSI measurement of subcarrier 7 will keep fluctuating in both empty rooms and human walkings. So it indicates that this subcarrier is not stable. As a result, we can see that the subcarrier 7 has the lowest score, indicating the lowest correlation with its adjacent subcarriers. Based on this insight, we select the 20 subcarrier with the highest score to extract the CSI features. To perform activity-based user authentication, we first need to determine the segments associated with human activities. The human activities will lead to variations in the wireless channel, resulting in changing CSI measurements. So we are applying short-time energy upon the CSI mmWave's moving variance to detect human activity. The first figure shows that both CSI's moving variance and short-time energy for 2 rounds of the same activity, opening a cabinet. It is obvious that the short-time energy can well capture the activity segments of the activity. In addition, we found that the peak of the fluctuating point in the short-time energy always locating in the center of the activity duration. We thus inspired to use a dynamic threshold to perform activity segmentation. Figure B and C shows the segment time series, CSI magnitude, and relative phase. We can see that our method for activity segmentation is effective, as they're both well locate the starting point and ending point of the user's activity. After from each activity segment, our system will extract representations for the user identity. Specifically, our system will extract 6 time domain representations with respect to CSI amplitude and relative phase. In order to provide final representation granularity for each activity, we first partition the CSI segments where the activity characteristics are embedded into several chunks of equal length. Then we extract the 6 time domain representations, including maximum, minimum, mean, skewness, kurtosis, and standard deviations. We also extract representation in frequency domain to capture the user's behavioral biometrics. We explore the short-time Fourier transformation to obtain the 2-dimensional spectrogram for CSI amplitude and relative phase. corresponding to each select subcarriers. Then 3 frequency domain features, spectrogram magnitude, perceptual spectrogram components, and spectrogram difference between 2 neighboring windows are extracted. After data preprocessing and feature extraction, we use a deep learning-based model to perform user authentication. We use a feature extractor to extract user identity features. The feature extractor consists 2 convolutional neural network models that learns a set of behavioral features to characterize both user identity and activity uniqueness. As illustrated in this figure, the CNN model consists of 2 3-layer stacked CNN, and in each layers of CNN, a convolutional layer with 2D kernels is used to calculate the 2D feature map, characterizing the user's behavioral uniqueness of activities and users. In addition, a batch normalization layer is used to collaborate the input data, aiming to mitigate the small-scale input variations, and a dropout layer is utilized to prevent overfitting. To realize reliable wireless sensing with deep learning, we also face a challenge, 2 important challenges. The first, when the users may conduct the same activity at proximate locations with small location variations. Second, the status of the physical environments, such as the placement of the furniture and home appliances, can vary from day to day. Both small-scale location variations and large-scale environment changes can lead to change of fluctuation patterns in the fine-grained Wi-Fi measurements, thereby causing the deep learning model unstable. To address these 2 important challenges, we propose an end-to-end domain adaptation-based approach to remove the environment and location-specific information in the collect CSI measurements. We aim to extract environment invariant features that discriminate among different users while being transferable in different domains. We define the domain as the user's locations and environmental status. So our objective is to derive an environment-independent deep learning model. We develop a deep learning-based user authentication model together with an unsupervised domain discriminator, which is built upon both label data, which is the Wi-Fi signals containing the user's biometric with labels, and also unlabeled data, the user's behavior data without labels collected in the new environments. We use such an unsupervised learning strategy to mitigate the impact of varying location and environment changes and achieve reliable user authentication. This well-trained deep learning model can then be utilized in a new environment to perform user authentication and achieving environment independency. To enable adaptive and practical authentication, we learn the domain invariant features from time and frequency representations. The input data are first mapped into a set of low-range behavior feature Z by using the feature extractor we introduced in the previous slides. Then a user recognizer and an activity recognizer are attached to predict the user identity and activity types. To remove the domain-specific information entangled in the extract features, we apply a domain discriminator to chain to predict the domain labels, for example, different locations and different environments. It seems to be contradict with our objective of deriving domain invariant features. However, by using an adversarial loss, the CNN model will be guided to derive features to spoof the domain discriminator, making the features in different domains indiscriminable. In this way, we can remove the location and environment-specific information encoded in the machine learning model. The key component of our strategy, as we highlight, is a domain discriminator. It is only used in the training process. and it forced the feature extractor to extract domain invariant features. Specifically, the domain discriminator consists of two fully connect layers using leakage value as adaptation functions. By applying a negative factors lambda, we can see that there is a negative factor lambda here. It can the extract feature extractor, the feature extract with the feature extractors will optimize to spoof the domain discriminator, making the features learn in different domains indiscriminable through each other. And at the same time, they will preserve the discriminative of different users and activities. In this way, we can authenticate the user, identify the activity while making the features indiscriminable from different domains. In this way, we can achieve environment-independent user authentication and activity recognitions. In addition, to detect unauthorized user, we train the user recognizer to differentiate one legitimate user to all other users. This is for spoofing detection. For example, detecting some users that is not in the profiles, which are likely to be the illegal users. In the training phase, we randomly select two users as spoofer to guide the user recognizer to detecting the legitimate user and other users. And in addition, we select the data of the same set of users from the target datasets to extract environment invariant features, making our spoofer detection scheme robust to different domains. So we summarize our systems in these slides. Our system first takes time series CSI measurement from Wi-Fi link between smart devices. It then extracts frequency domain components of CSI amplitude and relative phase to determine the CSI segments. We use both CSI amplitude, relative amplitude to extract both time and frequency domain representations. And after data processing, our system will use two CNN models with 3 convolutional layers to extract time and frequency domain features, which characterize the user's identity and activity uniqueness. To make the CNN model environment independent, our system will employ an unsupervised domain discriminator to remove the domain-specific information from both time and frequency domain representations. The domain discriminator is optimized to predict the user's location and environment status based on both labeled and unlabeled data. By simultaneously training the domain discriminator and the CNN model with an adversarial loss, the CNN model will learn to extract features that is independent to the environments and the location. We conduct extensive experiments to validate our systems. We use 2 Dell laptops equipped with Wi-Fi NIC to emulate the IoT device in smart environments. One laptop is used as the transmitter and the other laptop is used as the receiver, as we can show in the slides. Both laptops are equipped with an Intel 5300 network interface card, which will check and report the CSI at 30 subcarriers. The experiments are conducted in a residential apartment and an office with different sizes. We conduct experiments with 10 and 5 users in these 2 environments, respectively. To evaluate the system's dependency to the environments, for the 2 environments, for the 2 rooms, we collect data under 3 different furniture placements. The furniture placement is where we refer to as the environments in these presentations. For each environment, we move the desk, chair, sofa at least 3 feet to simulating the large-scale environment changes. When collecting data in the office, we also ask the 5 users to perform 3 activities with location variations. The data will collect activity at 4 proximate locations at 1 foot away from each other. In total, we collect 3 datasets of location variations and 4 datasets of environment changes with 20 rounds per activity per user for each dataset. We separate the collect dataset into source dataset and target datasets. The source dataset is used for training, and the target dataset is used for unsupervised learning. We first show the performance of our system on user identification and activity recognition with random split. This is an environment dependent result. Our system can achieve over 93% average accuracy on simultaneously recognizing both the activity and identity of the user. Furthermore, we find that our system can achieve over 93% accuracy on identifying each individuals. Then we showed our environment-independent results. This figure gives the user identification performance under large-scale environmental changes. Our approach can achieve over 87 and 83% average user identification accuracy for different settings. We can find that the results are 30% higher than the CNN baseline model. Under domain variations, the proposed domain approach can achieve over 91, 83, and 84 average identification accuracy using 3 different data splits, which are 31% higher than the CNN model. Finally, we evaluate our system under spoofing attacks. For random attacks where the user used different activity from the legitimate user, we can find that our system can achieve close to 100% true positive rate and lower than 1% false positive rate across all settings. And for the mimic attack, where the adversary performs the same activity as the legitimate user, our system can still achieve a high true positive rate and less than 2% false positive rate. The results show that our system is effective in defending against different types of spoofing attacks. So in this work, we designed a device-free user authentication system by extracting unique biometrics from CSI measurements. We address 2 important problems: small-scale location variation and large-scale environment changes with a domain adaptation-based scheme. We designed an unsupervised domain discriminator to derive environment-independent CNN model for activity recognition, user identification, and spoofing detection. We conduct experiments in indoor scenarios to demonstrate the effectiveness of our system under various degrees of environment dynamics. So during my PhD study, my research has been published in many selective venues, which includes 7 journal magazines, and also 16 conference papers, and also 4 papers as selective venues. I express my deepest thanks to Professor Chen for all his help in my PhD studies. And in the future, I would like to point out a few future directions that I would explore in the future. I would like to explore. So the first is that this is a collaborative project. The speech privacy attacks using the mmWave radar. The speech privacy leakage has long been a public concern.
Now, probably you can point out this is a collaborative work with Professor Petropoulou and also Professor Wu. And
Yes. Thank you for pointing it out. Yes.
Together.
Yes. This is a project that we are collaborating with Professor Wu and also Professor Petropoulou to explore the mmWave radar to perform speech privacy attack. The speech privacy leakage has long been a public concern. So an adversary may steal a user's private information on enterprise financial and intellectual properties or an individual's privacy information, which could lead to catastrophic consequence. So existing attacks on eavesdropping mainly rely on physical context or line of sight between the sensors and the sound source. So in the future, I would like to discover a new form of speech privacy attacks that sense the minor speech-induced vibration, a common room objects, by using mmWave. We find that as the user speaks, the speech sound waves will trigger the neighboring room objects, leading to minor vibrations. We aim to use mmWave radar, which has a millimeter level sensing resolutions, to sense such vibration and recover human speech. We aim to integrate a Phased-MIMO radar, which have the capability to perform beamformings and also fuse the multiple antennas to achieve high resolution sensings. Such an attack enables us to capture human speech, even the radar sensors and the human speakers are not in the line of sight. In addition, I would like to explore a new user authentication scheme on AR/VR headsets. AR/VR has shown promising potential in many applications, such as virtual banking, shopping, healthcare, and more applications will become available in recent years. Such a growing chain will make a face-mount AR/VR device inevitably contain private and sensitive information, such as contactless credit card number and merchandise ordering information. And a secure user authentication scheme is desired. I plan to investigate using facial vibrations when the user speaks to perform voice authentication.
Yeah, I think you also need to say that this work is collaborative with Professor Wang.
Oh, yeah. Thank you for pointing out that. Yes. And this is our ongoing project with Professor Wang, and also Professor Nitesh Sessner in the Texas A&M University. So this is our ongoing project also. So we aim to use the facial vibration originate from the vocal cord and propagate through the user's muscle, tissue, and bones to capture the intrinsic biometrics for user authentication. The facial vibration compared to traditional voice authentication scheme, the facial vibration have advantage because it will not expose to public. For example, when we're placing a hidden microphone close to the user, the facial vibration will not propagate through the air and record by the microphones. And such a distinctive characteristic will make face vibrations more secure compared to traditional voice print and over-the-air recording by the microphones. So I would like to express my deepest appreciation to my advisor, Dr. Ying Chen, for his kind and patient supervision during my PhD study. And I also want to thank Dr. Pachapulu and Dr. Wu and also Dr. Wang for your patience and time. Thank you very much.
Okay, yeah, thank you. Thank you for the presentation. And so we'll do this in two phases. So the first phase, I'm going to leave this to the students, to the audience, to see that if they have any questions. And the second phase is that I would think the committee members will, of course, in the first phase, committee members can also ask questions. Then in the second phase, that we're going to let the students leave the room, and then the committee members will just, ask you questions. Okay. Sure. So I like to see that if any students or committee members would like to ask questions at this moment.
Hi, Cong. Actually, I have a question I want to ask.
Yes.
Yeah. So, can you go back to the second project that you introduced for the data processing part?
Second project or? Yeah,
the second project. I think it's something about here. Like the part that you introduced, the time and frequency domain data processing. Something about like the relative amplitude and the three.
This one? Is this one? Relative phase. This is relative phase.
No, sorry, not this one. Yeah, because you mentioned a lot of projects. Actually, I'm a little.
Yeah, so probably you can, Carlo, you can say that which project you like Cong to talk about.
Yeah, so I think you just passed through that. So the one that you do the data processing, and then you feed the both time domain feature and frequency domain feature into the CNN neutral. Yeah, I think it's the one slide before this.
Okay. Yeah.
Yeah. So the time domain representation. So you said you kept compute 6 statistic representations in each chunk.
Yeah.
So like, what is the insight? Like, why you choose these 6 statistics? Like, for example, I know like the mean is the and the variance, the skewness, they actually related to the moment generation function. But I would like to ask like why you go to the 3rd and the 4th moment generation function, like the cortices, and you didn't go to the even higher. Like, is this based on the experiment results, or is if there's any insight of this?
Okay. For the statistic insight, because the first we survey a border areas of the different type of features, and we find that these 6 features they are most discriminative among different users. We perform feature engineering to identify the features that are discriminative across different users. That is through our preliminary studies on the features. And also for these statistic features, they characterize different perspectives of the signal. The signal itself is equal with the user's representations. So the maximum, minimum mean there are features that can characterize the overall signal properties. While the standard deviation, skewness, kurtosis, there are statistic assessments on the signals. They capture different perspective of the signals, and we find that these 6 features they are most effective compared to other features we explore. They are discriminative across different users.
So basically, from my understanding on this plots, because the blue line and the red line, they are highly distinctive. So these 6 features can be used as the the feature that to discriminate different users' properties. Am I understanding right?
Yes, because they are discriminative.
Okay, I got it. Thank you very much. Thank you for the explanation.
You're welcome.
Yeah.
I can also ask a question.
Good.
Very good work, Cong. Very nice presentation. Definitely a large body of work. I'd like to ask about the CSI that you are estimating.
Mm-hmm.
So CSI changes can change very fast with movement, depending on the space, of course. If you have people moving, so how long does it take you to retrain your model for CSI? This can determine how long can the environment change. In which case, if your method is applicable to this environment.
Yes. I want to confirm that. So your question is that the CSI collects in different time. They have different variations. For example, we collect data in the morning. Maybe the pattern change a little bit in the afternoon.
Not only that, but between different points. I guess you don't know where the user will be in the room, right? So you have to find the CSI in all possible points, and CSI can change from point to point. Widely, right?
So first, I think this is a problem of how we detect the user, whether the presence of the users. For the presence of the users, we will use a variance space, because our observation is that as the human perform the activities, the CSI will have higher level of variance. So by examining the variance level, we can detect whether a user is performing motions or not. So our authentication scheme is based on the user's behaviors, which is the user need to have some motions for us to process. So in this case, we detect the user's motions based on CSI's variance, and then we determine the corresponding segments to perform user authentication.
Right, but if you your user is in a different position in the room, the CSI will be different.
That's right. That's right. I think
maybe
yes.
Even if he's moving, the variance of the CSI could be smaller.
Yes, yes. That is also one problem that we used our domain adaptation scheme. I agree that because the Wi-Fi signal, they capture the propagation is omnidirectional. Yeah, the Wi-Fi transmission is omnidirection. They can carry the environments and also user's position and also the user's characteristic itself. So and our methods of domain adaptation is actually to remove such variations corresponding to the user's location and also the environments. So the idea is that we can extract position invariant features by using domain discriminator. For example, when we're training the data in one environment with the labels to train the DNN, and when in the testing phase, if we collect a data in a different positions compared to the training environment, we can use domain adaptation techniques to remove the position-specific information. So that our model trained in one position can be applied to another position. So that's the idea. We use domain adaptation to adjust such location and also the environment variation if the furniture placement of the room are changed. So our strategy is to use domain adaptation.
Thank you.
You're welcome.
Yeah, and actually I want to also add on that. Yeah, domain adaptation is like one step to it, right? But there are also other variations, like as Professor Petropolo pointed out, it's possible that the channel state information varies a lot as the time goes on, right? So it's also being affected by the time domain features. So in that sense, I think now ongoing work will also work on some statistical features that, for example, one of the conformal prediction work that you're currently working with another student, Kailong, that try to address environment changes and also the time variations at the same time.
That's right. Thank you very much for the further explanation. That's made it much more clear. Thank you.
Maybe I can ask one question. So, so when you in your project then using user activity for user identification, do you have any insights of what kind of user activities that are especially good for user identification? Maybe some categories. What type of activities that you have tried before, and do you have any observations of any specific activities that are good for user identification?
Yes, thank you, Professor Wang. That's a very good questions. So in our study, we actually conduct experiments with two types of activity. One is stationary activity when the user is, for example, perform activity at a location, at a fixed location. And also walking activity where the user's location is changing across times. For both type of activity, we show that our system can achieve high user identification accuracy. And for our experience, we find that because our authentication system is based on human behaviors, which also highly relate to the human motions. The larger scale the motions, the more stable the CSI measurements and also the potential high accuracy of our systems. In this case, the walking activity, for example, when users walk from one position to another, in this case, we find that the user authentication accuracy are normally higher and also the more stable. So this is based on my observations. But our system can also apply in the stationary activity when the, for example, when the user's opening a cabinet and fetching some documents from the table, and also our system can also have high accuracy on that case.
Okay, thank you.
Thank you for the question.
Okay, do we have any other questions in this open session?
Yeah, Cong, I have a question. Yeah, thank you for your nice talk. Yeah, my question is that how did you collect the data from the user? Take example, your one project is to measure the facial variation, right? So I think that each user will wear the AR/VR headset in a different position, even for each user. In different day, the position, localization in the face may be slightly different, right? So does this impact your performance? And how did you eliminate or mitigate this impaction for your performance?
Okay, thank you for the question. I think you are talking about the ongoing project that we use the AR/VR for user authentications. So in that case, we use the Oculus Quest, which is a commercial, one of the most popular AR/VR headsets, to collect the data. So we designed an app to collect the motion sensor data, including the accelerometer data and gyroscope data, and we use them to capture the facial vibrations. And I agree that different positions, wearing position, they could have problems. They could have different minor scales variations to the facial vibrations. But we've also, in that case, we are still working on extract features through feature engineering to extract the features that are consistent across different variation, because when you use a wearable headset, it may have minor variation, position variation, but that will not significant difference. In that case, we can still through feature engineering to extract the position independent features from the headset to perform user authentication. I think that is feasible.
Okay, thank you.
You're welcome.
Okay, sounds very good. Okay, do we have any other questions for the open session?
Perhaps I can ask one quick question. So sort of related to Bing's previous question, I think a lot of your projects are very interesting, how they can, especially for the AR/VR authentication, since they may use like motion sensors like the accelerometer or gyroscope or sensors like those. My question is, for some users, perhaps they may have some medical condition, maybe Parkinson's disease or Tourette syndrome, where they have some involuntary motions or things that they cannot control. So my question is, how would these systems maybe handle these types of users if they may have some occasional involuntary movements? Can you account for these people?
Right. Actually, I have not considered these cases before. I think this is an interesting problem. So based on my experience on exploring this topic, I think one potential solution is that we need to design a scheme to differentiate what is the normal movements and also what is the segments, for example, data segments that is corresponding to human speech. I think the Parkinson's disease and also have such minor, they will mainly induce the low frequency movements, because human speech movements, they are normally below 80 Hertz. Well, compared to the target, the data we are trying to explore, which is associated with the facial vibration of speech. When the human produce the speech, the vocal cord will produce the high frequency vibration, which is normally over 100 Hertz. In that case, we can differentiate the high frequency voice related facial vibrations with the low frequency movements that may be irregular movements. In that case, we can differentiate these two type of motions through frequency domain analysis.
Mm-hmm. Yes, I see. Yes, that's intuitive. Thank you for the answer.
You're welcome.
Okay, great. Okay, so I think, do we have any other questions for the open session? If not, so I will ask all the audience to leave the Zoom meeting.